Dislocations are linear defects in a crystal structure. They are areas where atoms have permanently shifted in reference to groups of atoms around them. Dislocations have a tendency to strengthen the material they are put into. Vacancies and self-interstitials are point defects in a crystal lattice. A vacancy is a hole in the lattice, and a self-interstitial is an atom which has been forced in between atoms in a regular lattice. Dislocation motion is plastic deformation by means of slip. Slip happens along a crystal plane and can either be transverse or rotational. Transverse dislocations are termed edge dislocations, and rotational dislocations are termed screw dislocations. Berger's vectors can be drawn on a crystallographic plane for both the edge and screw dislocations. For an edge dislocation, the Berger's vector is drawn parallel to the dislocation motion. For a screw dislocation, the Berger's vector is drawn parallel to the dislocation. The Berger's vector is always parallel to slip.
Grain boundaries are locations of large atomic mismatch between different grains. This creates repulsive stress fields that oppose continued dislocation motion. Dislocation pileup occurs as clusters of dislocations are unable to move past the boundary. However, as the number of dislocations increase at the grain boundary, greater repulsive stress fields are generated along the same boundary. These repulsive forces act as a driving force to reduce the energetic barrier for diffusion across the boundary, such that additional pileup causes dislocation diffusion across the grain boundary, allowing further deformation in the material. There are a few countermeasures against this phenomenon. Decreasing grain size decreases the amount of possible pileup at the boundary, increasing the amount of applied stress needed to move a dislocation across a grain boundary. The higher the applied stress needed to move the dislocation, the higher the yield strength. Thus, there is an inverse relationship between grain size and yield strength. Grains reacting to stress. Within each grain, the individual atoms form a crystalline lattice. Each atom will have a certain number of close neighbors with which it shares loose bonds. The number of neighboring atoms depends upon the structure of the lattice. When stress is applied to the metal, the atoms will start to spread apart. The atomic bonds stretch and the attractive forces between the atoms will oppose the applied stress, like millions of tiny springs. If the metal has not yielded, the inner atomic forces will pull the metal back into its original shape when the stress is removed. Grain size has an interesting effect on the required stress in order to achieve plastic deformation. Plastic deformation is normally the large-scale movement of dislocations through a material. Grain boundaries hinder the movement of dislocations. Smaller grains have more grain boundaries that impede the movement of dislocations through a material. Hence, smaller grain size means harder material, and larger grain size means a more ductile material. Dislocation stack-up and dislocation grain boundary interaction. In grain boundary strengthening, the grain boundaries act like pinning points. Pinning points impede the free movement of dislocations through a material. Dislocations will typically travel or move through a material when a little stress is applied. The large-scale movement of dislocations results in plastic deformation. Most dislocation stack-up or pile-up will occur at grain boundaries. This is due to the orientation of the grains themselves. Typically, grains will have a unique orientation compared to an adjacent grain. The lattice structures will not perfectly line up, forming a grain boundary. Grain boundaries are very disordered as compared to the inside of a grain. This prevents dislocations from easily breaching the grain boundary, changing orientation, and then traveling into an adjacent grain. Enough dislocation pileup eventually leads to dislocations jumping the grain boundary and traveling into adjacent grains. This will lead to more plastic deformation in the material. Grain boundaries, low angle and high angle. Grain boundaries are typically broken down into two categories. The first category is low angle boundaries, also known as subgrain boundaries. Low angle boundaries are ones in which the misorientation between two grains is less than 15 degrees. These low angle grain boundaries can have an array of dislocations, and the properties of this are a function of the misorientation. The second category of grain boundaries is known as high angle boundaries. High angle grain boundaries have misorientations between two crystallites that is greater than 15 degrees. The properties of these grain boundaries are independent of the function of the misorientation.
Hey, it's Avery. I'm doing this because the assignment requires all group members to narrate, so here I am. I did all the editing, and hope you enjoyed that wacky, wild video that we just made. Bye-bye.